in this session, we're going to explore stretching and compressing, and we're talking about functions. So referring to our basically our library of functions or our basic functions, we're going to see how those graphs can be transformed in these particular ways. First, we're going to look at vertical stretching and compressing, and I usually like to use things that we're familiar with to start our journey into the unknown. So here's a parabola, the graph of y equals x squared, or f of x equals x squared if you like. And what we're going to do is, on a new set of axes, sketch the graph of g of x equals 1/2 x squared. I think a good starting point would be to consider XY table of values, but we're going to get away from that, I think, well, by the end of the video, of course. But for now, we'll just throw in a couple of values and see what happens when we square it and then cut it in half for each value. 0, of course, will evaluate to 0. 1 will evaluate to 1/2. And 2, when we square that, we get 4. Cut that in half. Evaluates to 2. Just for good measure here, we're going to throw in -4. And when we square that, we get 16. Cut that in half, we get the value 8. So let me go ahead and put these dots, let me plot these points. Okay, so I've plotted these points, 0, 0, 1, 1/2, 2, 2, and -4, 8. Clear that up. And then let's go ahead and use the symmetry of the parabola and plot the corresponding points opposite the y-axis, which we can do because in the vernacular of functions, this is an even function. And let's go ahead and draw our curve. It should still be a parabola because the argument is x squared. However, you notice that the parabola that I'm drawing has a slightly different shape, and not just because I'm not perfect, from the one on the left. In fact, we can go ahead and compare them by superimposing one over the other. And what you can see is it's the same general shape, but this new one that we graphed is wider. And the reason for that is all of the y coordinates are half of what they would otherwise have been for f of x equals x squared. That's the effect of the 1/2 out in front. What this gives us is a vertical compression. In other words, all of the y values are compressed by a factor of 1/2. This is going to be the case whenever the coefficient in front of a function is less than 1 in magnitude. In other words, it wouldn't matter if it was positive or negative. Of course, the negative would have the effect of flipping the graph upside down, but as far as the way the shape would change, it would do so in the same way, vertically compressed. Let's look at our next graph. You'll see that I have, again, f of x equals x squared for comparison. What I'd like for you to do is, using an XY table, crank out a few values and see if you can draw the graph of h of x. Okay, so I've cranked out a few points, 0, 0, 1, 2, 2, 8, -3, 18. If you didn't use these same values for inputs, that's fine. You should still end up with the same picture I'm about to get. Let me go ahead and plot these points and their respective points due to the symmetry of this even function. And of course, there's not really any way that I was going to be able to graph -3, 18. Let's go ahead and connect these dots with a nice smooth curve. And we should still end up with a parabola because the argument is x squared, even though it has a 1/2 in front of it. And when I do so, I end up with a parabola that grows again at a different rate. But this time, because the coefficient is bigger than 1, that 2 makes the parabola grow twice as fast. In other words, the effect of the 2 as a coefficient doubles each y value. it doesn't move the graph up, but each y value is double what the y value is, the corresponding y value for x squared. So this is a what's known as a vertical stretch, and this is going to be characteristic of graphs, the expressions for which have a coefficient that is larger than 1 in magnitude. In other words, a -2 out front would give us a graph that is reflected but is still stretched. The effect of this on the parabola makes it look like that it's more narrow, but it's actually that it's stretched. And this kind of stretching and compressing is what's going to happen each time we have a coefficient out in front of the argument. Now we're going to turn our attention to another kind of stretching, horizontal stretching and compressing. And for this, we're going to use the greatest integer function. Let's get the closed dots and open circles as they should be at the ends of each step. And then, of course, the expression, f of x equals the greatest integer of x. And again, on a new set of axes, we're going to sketch the graph of g of x equals the greatest integer of 1/2 x. If you recall, the greatest integer function will give back the greatest integer that is less than or equal to the input. So let's go ahead and see if you can, using an xy table of values, come up with some points to plot, and I'm going to go ahead and help you out making your choices. Now, as you recall, when we looked at the greatest integer function before, we put in 2, 2.1, 2.5, etc. So let's go ahead and pick numbers that are like that, except I'm going to pick even decimal place numbers like 2.2 and 2.6. Let's say 2.8, 3, 3.2, 3.8, and 4. I think that'll be good enough for us to understand what's going on with this. So what I'd like you to do is figure out the output for each of these inputs for the function the greatest integer of 1/2 x using the order of operations, right? Start with simplifying the argument and then apply the greatest integer part. Now I got a bunch of 1s and then 4 evaluated to 2. If you're not sure why that is, let's just consider a couple of these. G of 2 is going to be the greatest integer of 1/2 times 2, which equals the greatest integer of 1, which is of course 1. And then if we have something like g of, let's say, 2.6, that's going to be the greatest integer of 1/2 times 2.6, which is equal to the greatest integer of 1.3, which is going to be 1, right? So that's why all of these, 2.2 all the way up to 3.8, evaluate to 1. 4, of course, evaluates to 2, and hopefully you can see why that is. Note that it looks like all the numbers between 2 and 4 are going to map to 1. So from 2 to 4, we're going to map to 1, and we're again going to have an open dot, open circle on the right, and a closed dot on the left. And if you do that with a few different numbers, then you'll find that the greatest integer function looks roughly the same this time as it did the first time we looked at it, except the steps are twice as wide as they used to be. Now, of course, we should be including open circles and closed dots on the right and left endpoints respectively, so let's throw that in. And as I said, we have this step function, but each of the steps has been elongated from the previous, the graph on the left. That's the effect of the 1/2 in front of the argument. It actually has the effect of a horizontal stretch, which I know is somewhat counterintuitive, and that's why we are going with the table of values to help us understand this. Let's see if we can figure out what's going on with another augmented argument, if you will. Here we again have the greatest integer function for comparison, and we're going to sketch the graph of h of x equals the greatest integer of 2x, and maybe you can guess how this is going to be different. we can use the table of values. And just so we can kind of see what's going on, we might use numbers like 0, a half, 1, 1.5, 2, and 2.5, and see what kinds of outputs you get for these inputs. Okay, my outputs are 0, 1, 2, 3, 4, and 5. Reason being, for instance, h of 1/2 is the greatest integer of 2 times 1/2. Went ahead and used a fraction so it wouldn't be confusing in there with the times. 2 times that. That is equal to the greatest integer of 1, which last I checked is 1. Okay, so that's how I got those outputs. And it seems to me like I might want just 1 or 2 more to kind of really seal the deal. So let me clear what I just wrote. And a couple more to help us see what's going on. Maybe a 4th and like 1 1/4. Maybe that'll help us. So the greatest integer of 2 times a 4th is going to be 0. The greatest integer of 2 times 1 1/4, well, let's write that out. H of 1.25 is equal to 2 times 1.25's greatest integer. 2 times 1 1/4 is 2.5. And the greatest integer of 2.5 is 2. So let's see what happens here. So I've plotted some of these points, 0, 0, 1/2, 1, 1.5, 3, for instance. Let's clear that up. And seems like it might be worthwhile to plot 1/4, 0, and 1 1/4, 2. And what we're going to see, I mean, this is still going to be a step function, but these steps are going to be a lot narrower. And in fact, our steps are half as wide as they were before. We still need dots and circles on the left and right ends of these steps. Excuse my imperfections here. That was a little bit like performing surgery with a chainsaw. In any case, hopefully you guessed correctly. The 2 out front of inside the argument, that 2x, has the effect of a horizontal compression, which is again counterintuitive, but if you can just remember ways that things are counterintuitive, then hopefully that should straighten things out. I don't know. When all else fails, we can use a table of values, and hopefully we'll start to get a handle on this as we work through some problems on our own. After all, that's what homework's for. Now we're going to move on to another kind of reflection from what we've seen in the past. See, I wasn't lying. Another reflection. And we have here the graph of f of x equals the square root of x, the square root function. And what we're going to do is use it for reference. We're actually going to sketch the graph of g of x is equal to the square root of negative x. I think that this is an example of one that would be useful to consider the domain. And let's recall that the domain of the square root function is from 0 to infinity. We want to keep it real. No negatives inside of an even index root. And if we think about the kinds of numbers, say from an xy table perspective, that we can put into g of x is equal to the square root of negative x, a couple of seconds thought, well, I don't know, sometimes it takes more than a couple of seconds. Sometimes folks look at this and they say, you can't put anything in it. And the answer to that is that's not really so much the case. What is the case is I can't put a positive number in place of x. But I could, for instance, put a -4 in place of x. If I did, I'd have g of -4, and that's going to equal the square root of the negative of -4. You see that negative simply says change the sign, right? And so g of -4 actually turns out to be 2. And so 0, of course, doesn't play the positive or negative game. But what I see here is that I need to include only negative numbers in 0, no positive numbers. So the domain of this function is actually going to be negative infinity to 0. And of course, in both of these cases, we have a square bracket at 0 because we are including 0. Let's get rid of those. The square roots of the numbers that I would put in, the square root of 0 is, of course, 0. Putting in negative 1 will spit out 1. Negative 4 evaluates to 2. And negative 9 evaluates to 3. And so here what I have is the graph of a square root function. And so it still has that shape of half of a parabola on its side. But as you can see, it's been reflected about the y-axis. And that's going to be the effect of having a negative inside of the argument. So if we have a coefficient inside of the argument, then we end up with a horizontal stretch or a horizontal compression. That's going to be counterintuitively obtained. But a negative is going to have the effect of flipping the graph about the y-axis. That's why I said it's another reflection. Now here we're going to have a few functions that we're going to graph. And what I want us to look at is what is the parent function, or the basic function, or as that one student said, the mother function. What is the location due to, say, a horizontal or vertical translation? Consider if the shape has been changed due to a stretch or compression. And finally, the orientation, whether it's been reflected either vertically or horizontally. So in the case of f of x is equal to 3 minus 2 times the quantity of x minus 1 squared, the first thing I notice is that there's a squared. That indicates to me that it's going to be a parabolic function. That's the parent function, if you will. This function looks like it would be easier for me to think about if I rearrange some terms, and sometimes when you do that, things become a little bit more clear. In this case, I'm going to write negative 2 times the quantity of x minus 1 squared plus 3. If I consider these in the order in which I've written them, I can see that I have a horizontal and a vertical translation. The horizontal translation is going to be 1 unit to the right. The vertical translation is going to be 3 units up. And you may remember in a previous video I mentioned a handle, and for a parabola I would say it's the vertex. So what this means to me is I'm going to have a vertex at 1, 3. Then a stretch or a compression. And I see that I indeed have a stretch. It's a vertical stretch due to the coefficient out front is bigger than 1 in magnitude. And then finally the orientation, and I can see that because the 2 is negative out front, I have a vertical reflection. What I have is a graph that's going to open slightly narrower than it would otherwise because of the stretch, and then that wasn't a good curve. So let me try to get a better curve here. And that'll be okay, I think. And if I wanted to, I could say find the y-intercept or the x-intercepts to get a better idea of how this is going to trace out. To tell you the truth, what I just did in my head was I pictured, I'm going to draw a set of axes up here just for a moment. I thought about what happens with the squaring function. And remember that it goes through the point 0, 0, and it goes through the point 1, 1. And then I thought about the effect that the stretch is going to have. And with a coefficient of 2, I know it's upside down, or negative 2, but with the absolute value, okay, the magnitude is 2, instead of going through the point 1, 1, it would go through the point 1, 2, right? That would be the effect of the stretch. And so I kind of flipped that upside down in my head. 1, 1 would reflect upside down. And instead of doing that 1 unit away, it's going to reflect 2 units down. So I was actually aiming for the point 1, 2, and then the point 0, 2. And before I'm done with this graph, let me just throw that back in here. In other words, we want 1 unit to the right and 2 units down. That's where I was aiming for. The reason for that, again, is that coefficient being negative 2. I know it sounds like I'm drilling it to death. What I wanted to say is if that coefficient had been, say, negative 3, I would have gone 1 unit out and then 3 units down. Negative 4, I would have gone 4 units down. If this had been instead a fraction, say negative 1/2, then I would have gone from the vertex 1 unit out and half a unit down. So whatever this number is, that kind of indicates where the point that would have been at 1, 1 will land. Hopefully that makes sense. If not, rewind the thing, watch the video a bunch of times, it'll start to sink in. Let's move on. Now we're going to look at the graph of, or sketch the graph of g of x equals 3 times the square root of 2 minus x. I can see the parent function, or the basic function, is the square root function. I can see a vertical stretch by a factor of 3 due to the coefficient of 3 out front. The argument, though, 2 minus x, is not what I'm used to seeing. I want to see the variable first. When I do that, I can write it as negative x plus 2. Notice the 2 is a positive term and the x is a negative term. So I'm going to rewrite the function here. G of x is equal to 3 times the square root of negative x plus 2. And I remember from a couple of examples ago, the negative in front of the argument is going to have the effect of reflecting about the y-axis. But don't be tempted right now to try to figure out any horizontal translation. I know that there's going to be one due to the plus 2 inside of the square root, but what we actually need to do is we need to factor the negative out of the argument. Now, because this is a square root, I can't factor the negative outside of the entire radical, but what I can do is rewrite g of x as 3 times the square root of the negative quantity of x minus 2. Notice that the sign changed on the 2 because I factored out a negative. So that negative, again, is going to give me a horizontal reflection at about the y-axis. And now I see that what I have is a translation to the right of 2 units. And so if the argument isn't of the form that I'm used to, like x plus 3 or x minus 2 or whatnot, then I want to do what I can to make it look like that. And not until I do can I really nail down the horizontal translation. Now the square root function, we know the shape of it hopefully, and this one's going to open to the left. Now I'm going to put down points that we won't actually be using just for reference. 0, 0, 1, 1, or negative 1, 1 I should say, negative 4, 2. This would be the shape of the regular reflected square root function, but a couple of things are going on. Number one, it's moved to the right 2 units. So this is going to go through the point 2, 0. Now these dots here, say at 1, 1 and negative 2, 2, would be the effect of the horizontal translation of each of these points to the right by 2 units. However, we have a stretch, a vertical stretch, and it's by a factor of 3. And so instead of the point at 1, 1, I'm going to have a point at 1, 3. That y value is going to be multiplied by 3. Instead of the point at negative 2, 2, I'm going to have that point at negative 2, 6. Again, it's being multiplied, the y value, by a factor of 3. That's the effect of the 3 as a coefficient in front of the square root. So let me clean this up and then reiterate. The points that define the shape of the square root function move to the right by 2 units. And then the y coordinates get multiplied by a factor of 3. Again, this isn't a translation. This time it's a stretch. And so I should be drawing a graph that looks like a very highly, tall, elongated square root function, and that's exactly what I'm going to have. So I've cleaned up the superfluous marks on my graph. I'm going to put a little arrow to indicate that this continues in the trend that it's in. And this is really what I mean when I say, and as I've said before, if you know the shape and you know where to put it, then you can draw the graph. Now we throw in, if we know how it's been stretched and whatnot, then we're good to go. Finally, for this page anyway, we've got the graph of h of x equals 2 over x plus 2 plus 1. Parent function. Maybe a little hard to see. The parent function is actually y equals 1 over x, which, as you may recall, is the reciprocal function and has kind of a curvy branch in the first quadrant and a curvy branch in the third quadrant. That's the shape that I'm going for. The 2 in the numerator, if I rewrote this, which you don't need to do, but I just want to kind of show you how I'm thinking of stuff, I have h of x is equal to 2 times 1 over x plus 2 plus 1. So the 2 is giving me a vertical stretch. And I think that the easiest way to see how that's going to work is by considering the point 1, 1. The y coordinate is going to be stretched by a factor of 2. In the denominator, we have that x plus 2. That's going to be a horizontal translation to the left, 2 units. And then outside of the argument, we have plus 1. That's going to be a vertical translation of 1 unit up. Now, we haven't really mentioned this at all, but the reciprocal function has a vertical asymptote along the y-axis and a horizontal asymptote along the x-axis. This, the only reason I'm mentioning it, gives me my handle, which is going to be where the two asymptotes intersect the origin. We'll see more about asymptotes down the road, but for now, we'll just say that they're kind of guides to show us how to draw the graph. So that point that's at the origin, not on the graph, obviously, it's just a place where two lines cross, is going to be moved to the left by 2 units and then up 1 unit. So that's going to be at negative 2, 1. Now what I'm visualizing here is this is where the y-axis would be. It's been moved, to the left 2 units, so to speak. And the x-axis has been moved up by 1 unit, again, so to speak. The graph of the reciprocal function goes through the point 1, 1. The graph of this stretched reciprocal function is going to go through the point 1, 2, except, it's been translated. Likewise, the bottom branch. And that's actually enough for me to be able to draw a reasonable facsimile of what this graph ought to be. So I'm going to reproduce the branch that I drew in the upper right down in the lower left. And as far as I'm concerned, we're good to go. I know this has been a long one, but hang in there, light at the end of the tunnel. Last slide, 2 more graphs. Use the graph of f to sketch the graph of a couple of transformations. And what we have here is kind of the squiggly graph that we've seen in a previous video. Except we're going to graph y equals 2 times f of x. That 2 as a coefficient out front is going to be a vertical stretch. And what that's going to do is that's going to double all the y coordinates. So what I'm going to do is I'm going to pick key points, figure out where they land, and then use that to draw my graph. So negative 5, doubling the y coordinate is going to be negative 5, negative 10. Negative 2, 4, doubling the y coordinate, it's going to land at negative 2, 8. And then likewise, that whole vertical, or that whole constant part of the line right there is going to have a value of 8. The y value is going to be 8. Didn't draw that long enough. And then the local minimum here has a y coordinate of negative 4. That's going to land at negative 8. Point of the graph is 5, 5. That's going to land at 5, 10. Again, what we're doing is we're just stretching all of the y coordinates. So if I can, wish me luck, draw this line here over constant down to the minimum, but what I'm trying to be very careful about is a couple of things. Number one, down here at the local minimum, it was not a pointy point, it was a curve. So I wanted to keep that. Number two, I didn't want to violate the function, the vertical line test. So it might have been easy to kind of do a poor job of it, like, letting our lines swirl around, but then I would actually end up violating the vertical line test. So I was trying to be very careful not to do that, and this is the stretched function. Finally, I know you're probably thrilled to hear the word finally. Same starting graph, and we're going to graph y equals f of 1/2 x. We may recall that the 1/2 inside of the argument is going to be a horizontal something or other, and if we remember that it's counterintuitive, then we can remember it's a horizontal stretch. The way I'm going to think of this is the original function goes from -5 to 5, like that's the domain of that function. As a matter of fact, if we think of this from the domain perspective, the domain is the set of x such that x is between -5 and 5. So if f of x means that x goes from -5 to 5, f of 1/2 x means that 1/2 x goes from -5 to 5. And solving this inequality will mean doubling everything, and so x will go from -10 to 10. So that's kind of the reason for why it's counterintuitive. The 1/2 inside the argument actually leads to a stretch. Ultimately, the stretch means that I'm going from -10 to 10, but we're going to keep all the same function values. This is not a vertical stretch. So the point that's at -5, -5 is going to become the point at -10, -5. Likewise, the point that's at 5, 5 is going to land at 10, 5. The constant bar is going to be stretched, so it'll be twice as long as it is. So why don't you pause the video, draw the result, and then check and see what I draw in just a minute. So what I've done is essentially doubled all of the x coordinates. -5, I landed that point at -10. Where x is -2, I landed that point at x being -4. Where x is 1/2, I landed that point at x equals 3, so on. So if I connect these dots, drawing the shape of the graph that is before me, with a nice curve down here at the local minimum, and then on up to the end. Let me clean that up just a tad at the end. This is the horizontally stretched function, and that is that.